Okay, right. So this is the last video, and I sort of hinted at where I was going. Again, the issue here is this. I mean, in the same way when I did my high-low method, I had something that looked like this, right? And remember, I knew what the units were, and I knew what the units were here, and then I said that you can find anything in between. In fact, you can extrapolate and find anything further on. And there's nothing different as to what's happening here. I know what the cumulative average time, or I can find. I'm told that, well, Oyen, if you start at 1 unit, and then if you go to 2 units, you can, using a certain percentage, you can find what's going on here. You can find out, and I double again, and I can find out what's going on here. Sorry, so this is, for example, 10 minutes and 9 minutes, and this is 1 unit, and this is 2 units, and this is 4 units, and I can know 8 units. The problem really that becomes is what happens in the in-between. You know, how do I find out what's happening there, and so again, in the same way where I had this whole y is equal to mx plus c curve to understand this, well, this curve has an equation. And if I know what the equation is, you know, where this is, and when we say y, remember this was y and this was x, where x is the number of units and y was the cost. And here where y is the cumulative average, x is the number of units, or the number of cumulative units. Yes, same thing. I'm just representing y on the y-axis and x on the x-axis. So y is equal to something, some type of equation that doesn't quite look like a straight line going downwards, but has a curve. And you are given this equation. And this equation is called y is equal to ax raised to the power, where are we? You're given this in the exam, raised to the power of b. So you need to get used to using the power on your calculator. So y is equal to ax to the power of b, and that's what this curve looks like. Someone's plotted this and says for any sort of point on this plot, on this graph, you can apply this equation, y is equal to ax raised to the power of b. Again, x is the number of units, cumulative units, and it says that we can find y and x for any of these. Now, what is a? So this is what this video really is about. Again, it's not just finding things; it's about the application. I mean, if I wanted to know how long it took to make the 15th unit, well, I could find. I mean, if I wanted to know remember, this is about cumulative. This is about cumulative. This is about total number of units. So if I actually wanted to find out what it actually took to make a particular unit, I would have to find the unit before it and the unit after it to find out what was going on, if that makes any sense. So if I wanted to find out how long it actually took to make the 16th unit, I would have to find the difference between the 17th unit and the 15th unit, that sort of thing. So it's about you applying it as opposed to just working things out. But remember, this is cumulative average, and this is total number of units that this is finding for us. So, where are we? So let's carry on with the problem again. Like I say, is that the doubling doesn't really help us. If we need to find out the 5th, we would kind of need this, and even a tabular structure can't help us. And this is what I've just written here, just that I couldn't find so it's the same thing. Y times a times is equal to a times x raised to the power of b. Now, what are these things? Now, x is as I said, the cumulative number of units. Y is the cumulative average time to produce x units. So y is an average. A is the time required to produce the first unit. So you'll be given that, the time to produce the first unit. And b is what's referred to as the index of learning. And b is equal to log r divided by log 2, where r is the learning rate. So percent, that'll be 0.9. So you need to find the log, for example, of 0.9 divided by the log of 2, and that's equal to your b. Remember, this is y is equal to ax raised to the power of b. So it's sort of the number of units raised to this b, but this b is equal to log r divided by log 2. So find this first, you get your b, raise your units to the b, multiply by a, and you get your y. So this is an example, I believe. The first unit of a new product is 100 hours. An 80% learning curve is known. So we can see we can gradually start to sort of apply this. We know that y is equal to a, which is 100, times 100x, if you like, raised to the power of log 0.8 over log 2. Yeah? This is our equation right now. This is our equation. So calculate the average time per unit for the first 16 units. So what am I saying? I'm pretty much saying, well, when x is 16, so y is equal to a, which is 100, x, which is 16, a times 16, 16 raised to the power of log 2 over, log 0.8 over log 2. I want to know what the average time it takes to make 16 units. If I know the average time it takes to make 16 units, I can find the total time it makes to make 16 units. So, you know, if I want to know how long it takes to make the 16th unit, all I need to do is find the total time it takes to make 15 units. If I find the total time to make 15 units, I have the total time to make 16 units. Well, like, the difference must be the time it took to make the 16th unit. I'm just always bringing in the applicative process here, and that's what they're really trying to test you. And I also want you to find the average time it takes to make the first 25 units and the time it makes the 20th unit. So here, let's just go to your, I mean, again, you just need to plug things into your calculator for these questions. So let's just do this. Let's just do this. I've already said that what we have is a scenario where, I mean, you can't see what I'm doing on the calculator, but the key point here is that these are what your equations look like. You need to be saying, for number 1, you need to be saying y is equal to 100 times 16 raised to the power of log 0.8 over log 2. So put this in your calculator, raise it to the power of 16, multiply by 100, and you'll get y. Do the same thing for b. We'll look at the answers in a second. 100 times 25, and again raise that to log of 0.8 divided by log of 2, right? And these are your answers. Let's go back and sort of see what these answers are. I've just taken this from your textbook, literally. So just allow me to do this. Almost there. Just going to get the answers. So what we have here, and this is a lovely kind of slide. Let me just make this clear. Okay, that won't let me use that. Let me try again. Right, here we are. So what we'll be doing, this b being 0.3219 is, if you put in your calculator log 0.8 over log 2, you will get 0.329. Then raise that 16 to that, and then multiply that by 100 and you will get 40.96 hours. And if you have the if you have just trying to forgive that commotion, sorry. I'm going to finish the video now. I don't want to sort of edit this. There's no point. Let's just sort of finish doing what we're doing. And I was talking about what happened. So all you're doing is you're plugging in the figures. Now, there's a question. The last question says, how long does it take to produce the 20th unit? I believe it is. Here we are. The time it takes to make the 20th unit. So what, if you remember what I said was to do this, and this is something we will do often, is that to find the time it takes to make the 20th unit, we need to find the total time for the 20th, total time for 20 units, which we have found, which we find here. When x is equal to 20, we plug in the figures, which is 100 times 20 times, so you can see the b remains the same all the time, and we have the total time for 20 units. Then we find the total time for 19 units and subtract them from each other, because that's the time it'll take to make the 20th unit. So that's really the theory there. The theory of what's going on. Yeah, I guess you can consider this child crying as humor at the end of this video to get you through the last couple of minutes. So let's just get through the last couple of ideas. So the key point here is that the pricing learning effect helps us to understand, kind of like life cycle costing, that we can't use the same cost throughout the time, that costs actually will fall. So if we base our pricing based on the first few units, we're going to have very high prices. And it also sort of says, well, maybe you don't need the people for as long as you do once you have them doing once they've gotten used to making the product. And generally, if a product enjoys the learning effect, then it means that if you start setting standard costs based on the original initial costs, well, then you have a problem. It's really about trying to get a balance because based on costing. So the question is, we're really saying that due to the learning effect, we can and be assured that costs will fall as we go along. But costs will reach a steady state because the learning effect only applies for a certain range of production. After a certain amount of time, the people can only go so fast. They'll get tired, and that after that, the average rate remains the same. Carry onwards from there. So I'll just highlight that key point because that is a big, that's an important point. Let me just get to a clean page, just to highlight what I'm saying here. That once you've got into a steady state, once you've got into a steady state in some capacity, what you will have is that you will have something that looks like this, for all the units, for the cumulative units after this, all your costs, your average cost will be the same. So you will no longer have a learning drop. You will just have the same average price as you go onwards. So we'll do a few questions in class to help us tackle this. But please conceptually make sure you're comfortable with what's going on with the learning curve. And I'll see you in class on Friday. Okay, great stuff. Thank you. See you then.